Okay, in this video, we're going to go over section 2.3, and this is on getting information from the graph of a function. So let me share my screen. And then open OneNote. So we're in section 2.3, and this is obtaining information from the graph of a function. So we're going to obtain information about the function from its graph, in other words. And so the first thing we want to talk about is, well, the first thing I'm going to mention is something we've already talked about, and that is the domain and range of a function. So we've introduced these as sets, but we want to look somewhat more geometric picture associated to these sets. So let me just remind you what these sets are. So here's a definition. So the domain is the set of all x values for which f is defined. So f is our function. So first of all, I should say we have a function y is equal to f of x. So f is this rule. It takes an input in x, and it gives you an output of a y value. And this is what enables us to plot these functions, that you compare these numbers together. You have the x value and its corresponding f of x or y value. So the domain of a function f is a set of all values for which f is defined, for which the rule makes sense. And the range is all of the corresponding, the range or the image y values. And we can actually define this set. So I usually call it image. So image and range are used interchangeably. So let's say the function is a function from A to B. So A is the domain, B is the codomain, and the image is a subset of B. And it's that subset which consists of all f of x, such that x comes from the domain. So you just take an element in A, plug it into the function, and put it in the set. So geometrically, this corresponds to the following. So we have the xy plane, or just the coordinate plane, and then we have the x-axis and the y-axis. And then A and B A will be a subset of the x-axis, B will be some subset of the y-axis. And then when you plot the function, it will be a subset of the plane, the coordinate plane. And so remember, we're plotting the graph of the function, which is also a set. And I'll remind you of what that is. It's all the ordered pairs x comma f of x, such that x is an element in the codomain, or in the domain. So just, for example, your set might be, the plot might look like something like this. Oops. So the domain will be this whole set right here. So this might be A. And that's the domain. The codomain is the whole y-axis. It's a copy of the real line. But the range is a subset. Notice it's almost like it's the extent of the oh no, I'm sorry, that doesn't go there. It goes up to We have this sort of this max value here. Maybe the max is right there, which is a concept that will come up later on, the maximum of a function. So the range of this function, the extent of it is this set right here. So this is the range, or image, as I call it. Oops. So the range slash image. Makes sense. So this is just a geometric way of displaying everything. And it's not usually the case, but sometimes we're given a graph of a function and we want to determine the domain and the codomain. But if you're given the rule that the domain is pretty easy to determine, the codomain, or I mean the range, could be a little bit more tricky to determine. Obviously, if you have a graphing calculator or something like that, it's a little bit easier to determine the range. So this is the way, the geometric way of viewing range, and domain, codomain, and the range, or the image. So the book gives an example, and I can't replicate it perfectly, but, and this is sort of a silly example because the domain is obvious. Once you write down the rule, the domain is obvious. In a sense, the range is also obvious. So our function is given by this. We wanted to find the domain and the range. So this is example 2 in section 2.3. And so you're given this function, then you're asked to plot it using a calculator, which you're not really required, but to have, although I will introduce you to this tool called Wolfram Alpha. That's freely available. And when you plug this function into the graphing calculator, it's going to look something like this. And on this calculator, graphing calculator is going to display some notches. So you'll have -2, -1, 1 and 2. And then this will be 1, and then right here might be 2. It's not perfect drawing, but you get the idea. But this will be displayed on your graphing calculator or some similar device. And then the idea is that, oh, it's from the picture, it's obvious what the domain is. The domain is this set right here. So that, or if we just call, or let's just use this notation. Oops. The domain of f is -2 to 2, and the range is this set here, this extent right here, which is also, well, it's not quite the same set, but it's just clear from the picture that this set is given by 0 to 2. So sort of a silly example, but whatever. It's just trying to illustrate that you can get some information about the domain and range from the picture. So that's one thing you can determine from the graph, a plot of the function. Another thing is solving inequalities. You can solve these geometrically, and solving equalities and inequalities. So, but in order to do that, we have to give some geometric meaning to what these equalities and inequalities are saying. They're saying something geometrically. So let me just write this down, and it'll be clear what it's saying geometrically. So the solutions, or I should say solutions, put this in parentheses, because there might only be one solution. So the solutions of the equation f of x equals g of x. So for example, you might have something like, I don't know, x squared plus 1 is equal to 2x plus 5. So this would be f of x, this would be g of x. So that's an example of something like this. So the way you read this equation right here, f of x equals g of x, is by saying that the solutions of the equation are the values of x where the two graphs intersect. What are the two? Yeah, the two graphs. I should just say the graphs of f and g intersect. That's what it basically means for when you have these two expressions equal to each other. That's what it's saying. It's saying that the graph of this one function and the graph of this other function, they intersect at some point. So for example, that would look like the following, or might look like the following. So you might have g looks like this, and then f looks like this. So right here we have a, say the x value is a, and this is b. So this top one is the graph of g, this bottom one is the graph of f. And what this picture says is that the solutions of f of x equals g of x are x equals a and x equals b. So that's the geometric interpretation of equations. Similarly, we have a geometric interpretation of inequalities. So the solutions, let me put that, so maybe there's only one solution there, there's no solutions. So the solutions of the inequality, oddly phrased actually, because that's assuming there are solutions, but there might not be. So the solutions of the inequality f of x less than or equal to g of x are the values of x where the graph of g is higher, the book says, or above oh yeah, I guess that doesn't make sense grammatically to say that. So higher than, I don't actually like the word higher. So it is above the graph of f. So what that might look like, and so notice here, this is just a strict inequality. You can say the exact same thing for less than or equal. So when if you were to have a less than or equal here, it would be all the values of x where the graph of f touches or is above, or the graph of g touches or is above the graph of f. So, but I'll just remove that for now. So you can easily modify the definition, or that's not a definition, but you can easily modify the observation. Yeah, so these are observations really, they're not definitions. Well, actually, let me just, I know, I'll just rewrite this. I don't know how to copy it. So G, say it looks something like this. F looks something like this. So they intersect at A, intersect at B. So here's G, here's F. So the graph of G is above F in this region here. So if we project down onto the x-axis, that'll tell us the interval, the solution set to this inequality. So if we project down on here, we see that, so they equal each other, G and F equal each other at X equals A and X equals B, so we don't want to include those. So we will just write a solid, a circle here with not filled in. But anything between A and B is a point where G, the graph of G is above the graph of F. So we can conclude from this picture that the solution set of the inequality f of x is less than g of x is the interval a comma b. So the book comes up with some examples, and I'm just going to use this tool here. This, you can find it for free on the internet. It's called Wolfram Alpha. So let me start over so you can see what's going on. wolframalpha.com. So you just open it up like this. You can use any browser. And we're gonna, this is example 3 in the book, and we're gonna solve some inequalities and inequalities graphically. So this will give you a little tutorial on how to use this as well. So type this in first, and then I'll explain what we're doing. So we're gonna plot 2x squared plus 3 and 5x plus 6. So now we're going to look at, we want to find out where 2x plus 3 equals 5x plus 6. But based on our observation, we know that that is equivalent to finding the points at which the graph of 2x plus 3 and the graph of 5x plus 6 intersect. So let's zoom in here a little bit. So we have an intersection point here, and we have an intersection point here. So this one's pretty clear, I think, to make out. It looks like they intersect at 3. This one's not so clear, so let's zoom in a little bit. And the way you do that is you want to plot the graphs on a smaller set. So we're going to say, let's plot it from -1 to 3. So yeah, definitely the graphs definitely intersect at 3. And this one is still a little hard to make out, but we can go on a smaller. So let's do -3/4 to 3. So it looks like they intersect at -1/2. So the problem is find the values of x for which this equals this. Geometrically, that corresponds to the points at which the graph of this intersects the graph of that. And we did that by using this graphing tool and just zooming in on here. And so the answer to that question would be -1/2 and 3. And of course, if you can do the algebra to verify that. So you would just set 2x squared plus 3 equal to 5x plus 6, and then solve this quadratic equation by factoring maybe, or maybe you could complete the square if you can't factor, or you could use the quadratic formula. Any one of those methods should work. One of the 3. So now, the next part of this example. So now let's zoom out. So I'm going to remove this part from -3/2 to, or 3/4 to 3. The next part of the problem wants us to determine where this function, where this expression is less than or equal to this expression. So let's just plot that first and go back here to the main plot. So we want to know where 2x plus 3, which is the blue curve, is less than 5x plus 6, less than or equal to. So obviously that's going to include the points where they intersect, which we just determined are -1/2 and 3. But we now need to go back and find out where it's 2x plus 3 is less than 5x plus 6. So if you now we just need to remember that observation I made a few moments ago, that solving inequalities, so if you have f is less than g, f of x is less than g, that's equivalent to finding, geometrically equivalent to finding where the graph of g lies above f. So in our case, we want to know, where does the graph of f of x, where is it above, at what points of x is it above 2x plus 3? And it's pretty clear, I think, from the plot that the purple line is above the blue line in this region. So that will correspond to -1 or -1/2 to 3. And you're going to include those endpoints. So let me just put this to the side, because this part of the example is a little more complicated. So as I said, we're in example 3, and now we're on part B. So we want to find where 2x squared plus 3 is less than or equal to 5x plus 6. So it's pretty clear from the picture that it's this region, and when you project down onto the x-axis, you get the following interval, and you include those endpoints because you have an inequality. So this is the solution set. So it's solution set of this inequality. I know this is much simpler than the other method, the algebraic method, although the algebraic method is a surefire method to getting the solution set, because you don't have to rely on human perception and this computer. In other words, there's these 2 degrees of, there's these 2 ways in which I can fail. I can fail in my perception, and the computer can fail me in some way. But this will give you a rough idea of what the solution set is. And if you can't, for some reason it's too hard to determine from the graph, you can always use that algebraic method to solve this inequality. Which you'll remember, how you do that is you throw all the terms on one side, because this is a quadratic inequality or nonlinear inequality. You have to throw all the terms on one side of the equation, and you have to do that table. You have to make that, or create that table where you determine the sign of the factors after you've factored this, of course. And so that will be the solution set of this. And then the last part, this is example, still the same example, but part C. Now we're asked to find the solution set to this inequality. So now to do this, we want to find where's the graph of this above the graph of that. Well, if we look at this, the graph of this is in blue and the graph of this is in purple, or I guess it's purple or magenta, or something like that. Well, it's clear that from the graph that this occurs in this region right here. So the blue curve is above the purple curve on this region and on this region. And notice that everything is where things are above or below is happening at the points where you can determine it are the points where intersection occurs. And those are what I call those break points. When you're solving these inequalities algebraically via the table, you first had to determine those breakpoints, basically the roots of the algebraic expression. And so those roots, or these intersection points, are helping us determine where the graph lies above or below the other one. So the solution set to this will be -∞ to -1/2. We don't include 1/2. So that will describe this when you project this part right here down onto the onto the x-axis. That this inequality will correspond to this, or that part of the graph will correspond to this inequality. And then when you come over here, you project down onto the x-axis. To describe this interval, you just look at the intersection points, as I said, project down here, and it'll be from everything from 3 and to infinity, not including 3. So this will be the solution set to this inequality. And as I said, it's much easier, but it's still good to know the algebraic method, because as I said, that will be a more certain way of determining the solution set. In fact, this is invalid. This is if you were asked to prove, if you were asked to determine the solution set to this inequality and prove it, this would be an invalid method of proof, because it's, as I said, computers always have this imprecision about them, and human perception has an imprecision about it. But the algebraic method that I introduced to you, that is a certain method to proving that this is the solution set to this inequality, or proving any given solution set to a given inequality is in fact the solution set. So this is actually technically an invalid way of arguing that this is the solution set to this inequality, but it's still helpful because it gives us intuition about what's going on. This is, you have to balance your intuition with algebraic methods and geometric methods. So this will give you a better intuition of what's going on. So the next thing I want to talk about, so this was solving inequalities algebraically, or I'm solving inequalities and solving equalities and inequalities geometrically. The next thing I want to talk about are minimums and maximums, and where functions are increasing or decreasing. So we're going to look at increasing and decreasing functions first. What does it mean for a function to increase or decrease? And how does this relate to inequalities and these geometric pictures that we've been looking at? So let me write down a definition first. So f is increasing. So first of all, actually, let me set, the book is not really terribly rigorous, so I think it's good to be a little bit more rigorous. So we have a function from A to B. So this domain is A and this codomain is B. And we're going to take some interval and it's going to be in B or in A. So recall, intervals are things of the form A comma B. It could be this. It could be that, or it could be that. So these are intervals, something of this form, and it sits inside the domain. So we say that f is increasing on the interval I. So it could be anything of this, one of these, an interval of this, one of these forms. So it's increasing on I if f of x sub 1 is less than f of x sub 2 whenever we have points that satisfy this. So we have the x1 is less than x2 in I. So x1 and x2 are points in I, and if they're less than, if x1 is less than x2, then f of x1 is less than f of x2. So in other words, the function is increasing in some sense if it preserves this inequality right here. Like if you were to apply the function to both sides of the inequality, it wouldn't shift the, it wouldn't change the inequality in any way. So in other words, if you have x1 and x2 are in points in the interval, so x1 and x2 are points in the interval with x1 less than x2, this implies that f of x1 is less than f of x2. So notice, as I said, if you have x1 is less than x2, then f in some sense preserves this inequality right here. It's like you can apply f to both sides of the inequality and it will still stay a less than. That makes sense. So that's a more dynamical way of viewing this inequality, that you have a function and it's acting on the inequality in some sense. And we say that f is decreasing on the interval I if f of x1 is greater than f of x2 whenever x1 is less than x2 in here. And similarly, we can rephrase it more concisely as if you have points x1 and x2 in I with x1 less than x2, this implies that f of x1 is greater than f of x2. So in other words, when you apply f to this inequality, it reverses it. So an example of such a function, of such a decreasing function, would be f of x is equal to negative x, right? Because when you multiply -1 by both sides of the inequality, it reverses it. So in other words, f is acting on the inequality by multiplication of -1. So this really is, you can really think about this function as acting on the inequality. And in this case, it's acting by multiplication by 1. So this right here is an example, a very simple example, in fact, of a decreasing function. And it's decreasing on the entire real line. So I, in this case, would be all of R, the whole real line. So this can be determined, again, you can determine this algebraically, but then we have there's a geometric interpretation to this, and it should be hopefully very straightforward what that means. So for example, we could have something like the following. Suppose our function is f of x is equal to x squared. And so the function is defined on R, and it sends, so the function goes from R to R, and we want to find the intervals on which f is increasing and decreasing. Well, since I have Wolfram Alpha open, I'll just plot it using Wolfram Alpha. So we're going to plot, I guess you could say y is equal to f, or y is equal to x squared. So we're going to plot y is equal to x squared. And it's clear, I think, that from the picture that we have increasing, that the graph of this is, or sorry, the graph of this is decreasing from -infinity to 0. So 0 is where things change, the behavior of the graph changes. So it's decreasing on the set, negative infinity to 0, and it's increasing on 0 to infinity. So now the next thing I want to talk about, and it's related, is I want to talk about our local maximums and minimums. So local max and minimum of a function. So first, the formal definition. So we have a function, again, it's from A to B. The first part of this definition is that the function, this is a definition of a local maximum. So the function f has a local maximum value It'll be clear what we mean by local in a second. And so that local maximum value is f of a for some fixed number a. If f of a is greater than or equal to f of x, when x is, and I'll put this in quotation marks because this is a precise term, near a. So if you find a value of a such that f of a satisfies its inequality, then by definition f of a is a local maximum value. And what do we mean by near? That's pretty simple. It's not too bad. Near just means that the inequality f of a is greater than f of x. Well, what it means, I mean, actually, it is, I want to say this. I want to say it means that there exists an interval, I should say open interval. This is important that the interval is open. So for example, it could be something, it could be, I don't know, say open interval B to C. So this is the open interval from B to C, everything, all the points between B and C. So near just means that there exists an open interval such that f of open interval in A. So we want the open interval to be contained in the domain such that f of A is greater than or equal to f of x for all x in I didn't give this the open interval name I. So there exists an open interval I. So for example, it could be of this form, B to C. Actually, this is really the only open interval in A, such that this inequality holds for all the points on the open interval. So open intervals are in some sense small. And this is the idea behind the term local. So we're not saying that this inequality holds on the entire domain. We're just saying it holds on a small part of the domain, namely this small open interval. And so now let's look at definition 2. This is a local minimum value, and it's going to be basically the same thing. So the function f has a local minimum value and the local minimum value f of a if f of a is less than or equal to f of x for x, again, in quotation marks, near A. So the term near can be explicated in the exact same way as I did up here. It means that there exists an open interval in A such that f of A is less than f of x on that open interval. So let's look at just a generic drawing for an example. So we might have a graph that looks like this. So right here would be a local max. This would be a local max. And this would be a local max. So these are local maximums. And then these right here, these are local minimums. And so the idea is that this point right here, for example, this is, let's say this is A, B, C, and then D. So this is f of A, this is f of B, this is f of C, this is f of D, this height right here. So f of A is not greater than every single other point on the plot, because like for example right here, this point is higher than this point right here, f of A. But it is, f of A is greater than every other value on a small neighborhood. Say here, this neighborhood of A right here. And we're not saying that it's f of A is greater than all the other values on every single neighborhood, just some neighborhood. Actually, that's not a term I use. This is all this right here is just topology. Actually, all this is just talking this field of mathematics called topology. When I say neighborhood of A, the point A, I mean an open interval containing A. So it's like this little tiny neighborhood of points. So this right here, this open interval right here is a neighborhood of A because it contains A. So neighborhood just means neighborhood of A, the point A is just an open interval, or more generally just an open set and the same thing of B, C, D, at any point you can talk about an open interval or a neighborhood of a point is just an open set or an open interval containing the point. So on this open interval containing A, this neighborhood of A, f is greater than all these other values because it's increasing up here. It's it's increasing on this side, and then it's decreasing on this side. So f of A is greater than the rest of these values right here. If I just take any other point in the open interval and try to trace it up, it's going to get to the height of this point is less than that point. And then the same thing, I can take an open interval right here and it satisfies the definition. So f of B is a minimum. I have this open interval right here and this open interval right here. So these are neighborhoods of, this is a neighborhood of B, this is a neighborhood of C, and then this is a neighborhood of D. And you can see that all these points either satisfy the definition of a local max or a local min. So this just is hopefully illustrates these, or hopefully this elucidates these definitions a bit. And I think that's really all. So we can go over this more, of course, on Friday. And I would like everyone to, keep track of things that you're not understanding in the videos, on the homework, write these down so that we can talk about these. And, over the video on Friday, we can, we can go into these things in greater depth. So I'm going to just stop here. I'm going to stop sharing and I'll stop recording and I'll upload this right now.